Right. So today we're going to be talking about neuronavigation with Kranion and virtual reality and how it can help advance the field of focused ultrasound. So first, some introductions. My name is Kippenhan. I'm a rising third year at the University of Virginia. I'm a computer science major and also a minor in data science. And my hometown is Falls Church, Virginia, which is in Northern Virginia. And a fun fact about me is I'm a rower. I actually rowed the team here at UVA. And you can see a picture here at the bottom of me rowing a competition. And I think Kathleen introduced herself already in the last presentation.
I already introduced myself, but in reiteration, the most important fact is that I like to make karate kicks. So before we begin, we'd like to define what is neuronavigation. Well, neuronavigation is the use of pre-existing images that were taken beforehand to allow doctors and physicians to navigate the physical brain. The most common form of neuronavigation that's done today is live MRI, where we take pictures of the MRI, we use a machine, and we look through your brain as we're doing a treatment. However, it has some disadvantages as you can't really do certain treatments such as neuromodulation and blood-brain barrier opening.
So a little bit about the purpose of the project. So what did we do? The major thing that we did is we implemented a network communication system between a neuronavigator simulated in Unity virtual reality and a program called Kranion. And this enabled Kranion to be used as a tool to assist in planning and conducting focused ultrasound treatment. And a little bit about why this is important, as Kathleen mentioned in the last slide. So neuronavigation is a less expensive more convenient option for patients and physicians rather than using a live MRI system, especially for types of treatments such as blood-brain barrier opening with drug delivery and neuromodulation, which often require repeated treatments, which is more difficult to do at the same time as an MRI scan. So the first part of this project, the two programs is Kranion. It's a transcranial interactive focused ultrasound visualization system, which you can use to calculate and plan treatments. You can import a combined image of CT and MR data, as shown in this screenshot here. And you can use personalized planning functions, such as creating planned sonication points at various points throughout the brain. And next, this is a VR simulation, which was actually made last summer by Interns. Here's a screenshot of it. So it was made using the Unity game development engine. And it's a simulation of a patient in a treatment room with a Medtronic Stealth Station neuronavigator. And the transducer you can see at the left side of the patient there. And the focal point is visualized as a red dot below that cone. And the user can grab the handle using a VR controller, and they can move the transducer focal spot around the patient's brain. And the MR images that you see on the screens behind and to the left of the patient will update live as you move the focal spot around. And this is just a picture of what it looks like to use the system. So this is me using it. So you wear a headset and you have a controller. And we're using two computers. So the computer running the virtual reality, you can see here. So center screen, that's what I'm seeing while I'm wearing a headset. And Kranion is running on the screen on the right side here. The reason we're using two separate systems is for this project is to conserve graphics resources, because running both the virtual reality and Kranion on the same computer at the same time is fairly graphics intensive and not really feasible. And in the clinical setting, this makes sense because Kranion would represent the actual treatment planner, and the virtual reality would represent what's actually happening in the treatment. And we have a video demo.
So to begin, when we enter both Unity and Kranion, we can put in the server IP address and a server point, which will allow the two computers to connect them to each other. Once connected, the first thing you can do is toggle tracking, which means in Unity, once you grab the transducer and move around a patient's head, you'll also see it move around in Kranion in real time. So as you can see, Kranion And then another thing that we've also implemented is that once you disable toggle tracking, is that you can reset the position and then immediately start your planning. So when you want to plan treatments in Kranion, you can click on any spot around the brain and create sonication points. And then you can add them into the Unity environment where they'll show up. And you can perform treatments or you can remove them as needed. So once the treatments have been set, you'll see them immediately and they're flashing green and white to allow the user to see them more easily. You can remove one target at a time, or you can remove all of them if needed. And we'll send the targets again so you can see how treatment is being performed. When you press a button on the controller in Unity, it will apply a blue ball, which will make the green target stop flashing, indicating that treatment has been performed. And finally, once you're done with the system, you can press the disconnect button, or you can shut down the Unity Center, which will safely remove the connection between the two.
Okay, so in conclusion, just to remind you about what we've done again, we've made we've connected both the Unity VR simulation and Kranion through a network socket communication. And we have created a tool that can serve as a basis to allow physicians to conduct more efficient and cost-effective treatments, which will make focused ultrasound more available to patients. And we also learned a lot through this process. We learned about working with Unity and virtual reality, as well as some matrix transformation math, network programming, scripting with a programming language called Groovy, which is what we use to add on to Kranion. We also learned a lot about Kranion, as well as GitHub, which is a software version control system.
For acknowledgements, we'd like to thank Mr. Renovich, Dr. Cassell, and our advisors and the other interns who contributed to this project, and the staff who helped us greatly in supporting us in our journey throughout this internship. Thank you.
And for everybody that's interested, we have a live demo of the intern room if you'd like to see it at any point for today. Any questions?
I don't see any questions on the chat either. So thank you both. And